Hello friends, welcome to the Ontam Coach YouTube channel. Is this world truly as it appears to you? Does reality change when you observe it? Or do you create your own reality? Can future events determine past events? Or is time just an illusion? In today's video, we will attempt to answer such crucial questions related to our existence with the help of quantum physics and Advaita Vedanta. Quantum physics is the branch of physics that studies the behavior of particles at atomic and subatomic levels. The theories and numerous experiments of quantum physics challenge our traditional understanding of reality. Quantum physics has unveiled a new dimension of reality that has entirely transformed our perspective of the world. Let's first discuss the most popular experiment in quantum physics, the double-slit experiment. This experiment is a classic example in quantum physics that demonstrates the strange behavior of particles like electrons when observed. In this experiment, quantum particles like electrons are passed through two parallel slits on a plate and projected onto a screen. When these particles are not observed, they create an interference pattern of bright and dark bands on the screen, behaving like waves. However, when detectors are placed in front of the slits to observe them, their wave function collapses, and they behave like particles, creating two bright bands on the screen instead of an interference pattern. This means that the particles exhibit both wave-like and particle-like characteristics, a behavior known as wave-particle duality. The double-slit experiment also demonstrates the phenomenon of quantum superposition. Quantum superposition refers to a quantum system being in multiple potential states simultaneously until it is observed or measured. When a single quantum particle is sent through the two slits one at a time, it behaves like a wave and creates an interference pattern on the screen. This pattern suggests that the particle interferes with itself and passes through both slits simultaneously. However, when we use detectors to track the particle's path, the interference pattern disappears, and the particle passes through only one of the slits. This phenomenon indicates that until a particle is observed or measured, it exists in multiple potential states simultaneously. In simpler terms, the particle can exist in multiple possible locations at the same time, and upon observation or measurement, it settles into a definite state. Let me explain the double-slit experiment in simpler terms with an example. Imagine you are standing by a pond with binoculars, and an elephant is a kilometer away, heading toward the pond to drink water. The elephant has two unpaved paths to choose from to reach the pond. Now imagine that the elephant starts moving toward the pond, but you close your binoculars and do not observe which path it takes. Later, when you inspect the paths, you find footprints on both paths. This suggests that the elephant walked on both paths simultaneously to reach the pond. The next day, you stand by the pond again, this time observing the elephant with binoculars. You notice that the elephant chooses only one of the two paths to reach the pond. Upon inspecting the paths, you find footprints only on the path the elephant took. This means that when you don't observe the elephant's path, it takes both paths simultaneously, but when you observe, it chooses one path. This is similar to the behavior of particles in the double-slit experiment. When unobserved, a particle passes through both slits simultaneously, creating an interference pattern on the screen. However, when observed, the particle passes through only one slit, creating a non-interference pattern. The elephant example helps explain the behavior of particles in quantum physics, but how these rules apply to larger objects remains a subject of research. Sometimes, continuous observation or measurement of a quantum system can significantly slow its evolution. This phenomenon is known as the quantum Zeno effect in quantum mechanics. Continuous observation causes the state of the quantum system to repeatedly collapse to its initial condition, hindering its evolution over time. For example, if we continuously observe a radioactive atom, its rate of decay decreases. Phenomena like the quantum Zeno effect, wave-particle duality, and quantum superposition provide strong evidence that observation alters the reality of quantum systems. These quantum phenomena challenge deterministic and objective notions of reality, suggesting that reality is inherently probabilistic and subjective. Our consciousness shapes the form of our reality, we create our own reality. Next, let's explore another fascinating quantum phenomenon, quantum entanglement. This phenomenon reveals a profound aspect of space. Quantum entanglement refers to the interconnected properties of two or more particles, such that the state of one particle instantly affects the state of another, no matter the distance between them. For instance, if a photon is emitted from a non-linear optical medium, it splits into two photons with opposite polarizations. Until measured, the polarization of each photon remains undetermined. When the polarization of one photon is measured, the other photon's polarization correlates immediately, even if they are separated by a vast distance. If one photon is found to be vertically polarized, the other will be horizontally polarized, and vice versa. This correlation persists regardless of the distance between the entangled particles, demonstrating instantaneous communication between them. Let me simplify this concept with another example. Imagine you have a pair of entangled coins. You keep one coin with yourself and give the other to a friend who is thousands of kilometers away. One day, you both decide to toss your coins simultaneously over a video call. If your coin shows heads, your friend's coin will also show heads, and if yours shows tails, theirs will too. This happens every time you toss the coins. This is similar to entangled particles. When the spin direction of one particle changes, the spin direction of its entangled counterpart changes instantly, regardless of the distance between them. The coin example is a simplified way to understand quantum entanglement, as the rules of quantum physics for larger objects like coins are still a subject of investigation. Quantum entanglement shows that an event in one place can immediately affect an event in another place, no matter how far apart the two places are. It's like the beaches at both places having no space in between. As a result, the information of an event in one place reaches the other place instantly, or it could be that entangled particles are connected in space or perhaps part of the same system. Whatever the case may be, quantum entanglement challenges our traditional understanding of space. This phenomenon suggests that the separation between objects, or the difference in space, might just be an illusion. Now, we will question the existence of time by discussing the delayed choice quantum eraser experiment. The delayed choice quantum eraser experiment is essentially a modification of the double-slit experiment. In the double-slit experiment, particle detectors are typically placed in front of the slits to determine which slit the particles pass through. However, in the delayed choice quantum eraser experiment, the detectors are placed behind the slits to observe the behavior of particles after they have passed through the slits but before they hit the screen. This experiment introduces a special mechanism that allows us to decide, after the particles have passed through the slits but before they hit the screen, whether we want to store or erase the information about which slit each particle passed through. Since we make this decision after the particles have already passed through the slits, this is called a delayed choice. In this experiment, if we store the information about the particle's path, we find that the particles exhibit particle-like behavior and create a non-interference pattern on the screen. But if we erase the information about which slit the particles pass through, even though the path information was available for a while, the particles show wave-like behavior and create an interference pattern on the screen. The delayed choice quantum eraser experiment shows that our decision to store or erase the information about the particles' paths determines whether they will behave like particles or waves. This suggests that the future decision we make affects the past behavior of the particles. This influence of future measurements or observations on the past behavior of the quantum system is called retrocausality. Now, let me explain the delayed choice quantum eraser experiment in simple terms using the example of the elephant. Imagine you are standing by a pond again. This time, like last time, the elephant is standing a kilometer away from the pond, and to reach the pond to drink water, it has two muddy paths ahead of it. But this time, instead of a telescope, there are CCTV cameras on both paths recording the elephant's movements toward the pond. You can choose to either watch the CCTV footage or delete it without watching. But you can make this choice only after the elephant reaches the pond. Now, imagine the elephant starts walking towards the pond. The CCTV cameras record its movements until it reaches the pond. Afterward, you must decide whether to watch the video recording or delete it without seeing it. This time, you choose to delete the video recording without watching it. When you inspect the paths, you find the elephant's footprints on both paths, which means the elephant traveled both paths simultaneously to reach the pond. However, because you deleted the video recording, you didn't see the strange event where the elephant was in two places at once. To confirm this, you repeat the experiment. The elephant starts walking towards the pond again, and its movements are recorded by CCTV. After it reaches the pond, you decide to watch the footage. This time, you find that the elephant only traveled one path to the pond, and the footprints are only on that one path. This means that whether the elephant travels both paths or just one is determined by your choice to watch or delete the video in the future. In other words, the elephant, knowing your future decision to either watch or delete the video, behaves differently in the past. This is like saying that if future measurements store information about a particle's path, it will exhibit particle-like behavior and pass through only one slit. But if the path information is deleted in the future, it will show wave-like behavior, passing through both slits. I want to remind you that the rules of quantum physics and how they apply to macroscopic objects are still an ongoing area of research. The elephant example is simply used to explain the delayed choice quantum eraser experiment in simple terms. The retrocausality phenomenon shown by this experiment challenges the linear progression of cause and effect. Retrocausality challenges the traditional view of time, blurring the boundaries between past, present, and future. Now, let's try to understand the creation of the universe from the perspective of modern physics. According to modern physics, the entire universe is made up of 5 key components, 17 fundamental particles, 4 fundamental forces, space-time, dark matter, and dark energy. If we delve deeper and assume string theory to be true, we find that these 5 components are made up of tiny strings, or ultrafine threads. All these strings are physically identical, one-dimensional, and lack an internal structure. These strings vibrate in different patterns, and each pattern produces a different fundamental particle. The interaction between these vibrating strings leads to the creation of fundamental forces in spacetime. As for dark matter and dark energy, string theory attempts to explain them through vibrating strings, hidden dimensions, vacuum energy density, and modifications of gravitational laws. Thus, the universe is nothing but an expression of these tiny strings. So far, we have seen that quantum physics raises many questions about our understanding of reality. Through various experiments in quantum physics, it has been proven that the world is not exactly how it appears to us. Now, let's explore how Advaita Vedanta, an ancient spiritual philosophy, aligns with these modern discoveries to explain the ultimate reality. According to Advaita Vedanta, Maya has 2 powers. The first is the covering power, which hides the true reality, our Brahman nature. The second is the projection power, which creates the illusory world. Maya creates duality, causing us to see separate things in the world and making us believe in the diversity of this world. Just as the wave function of quantum particles collapses when observed, and we start seeing their particle nature, similarly, under the influence of Maya, our Brahman nature gets hidden, and we begin perceiving the illusory world. Just as quantum particles, which exist in a superposition state, collapse into a definite state when observed, the Brahman nature, full of infinite possibilities, gets hidden when we experience the world, and the illusory world, full of certainties, appears. This can be understood as the superposition state representing reality, and the definite state representing Maya. Endless possibilities are liberation, certainty is bondage. The world we experience is very different from the deeper truth hidden beneath. Quantum physics validates this idea of Advaita Vedanta. Advaita Vedanta denies the existence of time and space in the conventional sense. Regarding time, Advaita Vedanta believes that our concept of causality, cause and effect, is only an illusion. The retrocausality phenomenon revealed through the delayed choice quantum eraser experiment also challenges the linear progression of cause and effect. Regarding space, the phenomenon of quantum entanglement suggests that the apparent separation between objects may just be an illusion. Similarly, Advaita Vedanta believes that there is no difference between the observer and the observed. The apparent difference is superficial. At a deeper level, both are interconnected and one. Brahman is the ultimate observer. Brahman is the conscious element, and as we learned in the previous video, we are not separate from Brahman, rather, we are Brahman itself. Therefore, we can say that our consciousness shapes our reality. Our consciousness creates our universe. Just as string theory considers the entire universe as an expression of minuscule strings, Advaita Vedanta views this world as an expression of Brahman. According to Advaita Vedanta, all creations originate from the ultimate reality, Brahman. The interconnectedness of quantum particles, as seen in the quantum entanglement phenomenon, also points to the inherent unity of Brahman. Just as the quantum Zeno effect shows us that continuous observation halts the changes in a quantum system, making it stabilize in its original state, similarly, through regular self-reflection, the changes occurring in our practical life stop, and the soul stabilizes in its original Brahman nature. Now, let's reflect on this. What if everything we experience through our 5 material senses and mind is not the true reality? Our senses and mind entangle us in an illusory world, which is different from the true reality. The ultimate truth is Brahman. So, today, we've learned that the world we experience is a result of illusion, Maya. This idea is echoed by both modern quantum physics and Advaita Vedanta, which shows us that what we perceive is not the whole truth. In fact, the deeper truth behind it is Brahman, the ultimate consciousness that shapes everything. That's all for this video. See you in the next one. Thank you.